AP Pre-Calc. Today we're looking at section 1.8, which is all about rational functions and their zeros. And our learning target is I can identify critical values and solve rational inequalities. So remember, a rational function is just the ratio of two polynomial functions. So you can see we have a polynomial function in our numerator of f and a different polynomial in our denominator. And that's what makes it a rational function. So, two important traits of any rational function where your numerator and denominator have no factors in common, meaning we have already removed all of the wholes and canceled out any common factors. And once we have simplified our rational function, then we know anywhere that g of x equals 0, we have a 0 or an x-intercept. So when our numerator equals 0, that is where we have our x-intercepts. Which is the same thing as a 0. And then when our denominator equals 0, or h of x, that is when our rational function is undefined and where we will end up having a vertical asymptote. So when our numerator and denominator equal 0, those are what are called our critical values. And when we are solving rational inequalities, we have to identify both zeros and our undefined values. So our zeros and our asymptotes are our critical values or our critical points. So when we are solving a rational inequality, when we're solving anything, first step is always make sure it equals 0. And I put equal to in quotations because we're doing inequalities, so you're not actually going to have an equal sign, you'll have an inequality sign. But you want to make sure one side has 0 on it and all the rest of your rational function is on the other side. And where your rational function is, you want to make sure you have a single rational function, meaning only one fraction. Then we set our numerator and denominator equal to 0 to find our values or our critical points to include on our sign chart. So, before we continue with our steps, if we look at example 1, we can see that we do not have any factors in common, so it's already simplified. 0 is by itself, so we've done step 1. And then we do have a single fraction on the left, so then we want to identify where g of x and h of x equal 0 to identify our critical points. So from the numerator, when x equals 2, that would be one of our critical values. And then from the denominator, we get -6 and +3. So then our next step is to create a sign chart with those critical values. So we're looking at -6, 2, and 3. And as a reminder, we cannot be equal to our critical values from the denominator. So to remind ourselves of that, we're going to put holes over top of those two critical points. We can be equal to the critical value from our numerator, so we'll put a closed circle to remind us we can include 2, but not -6 or 3. So that is the beginning of our sign chart, and we have marked where h of x equals 0, so we don't include those. So once again, we can include the zeros, but not our vertical asymptotes. And then similar to when we did polynomial inequalities, we want to pick any value within each interval to test to see if those values within our interval are positive or negative. So if we start on the left side of our sign chart, to the left of -6, one example would be like -10. So if I think about substituting -10 into my rational function, -10 minus 2 will give me a negative number on top. -10 plus 6 will be another negative. -10 minus 3 will also be negative. And because we have 3 negatives, that entire interval will be negative. So our next interval is from -6 to 2. And 0 is a nice, easy number that falls in that interval that we can test. So 0 minus 2 would be a negative in our numerator. 0 plus 6 would be a positive number. 0 minus 3 would be a negative. And because we have 2 negatives, that interval will end up being positive, which is what we want. We want to be greater than or equal to 0. So then we keep going and test between 2 and 3, so like 2.5. 2.5 minus 2 will be positive. 2.5 plus 6 will be positive. 2.5 minus 3 will be negative. And since we only have one negative, that interval will be negative. And then lastly, we have 3 to infinity, so we can check 4, 5, or positive 10. We'll look at 5. So 5 minus 2 is going to be a positive number. 5 plus 6 is positive. 5 minus 3 is positive, and all positive means we're going to be positive. So once we test our values and determine which intervals are positive or negative, we go back and we interpret our sign chart to identify the intervals that satisfy our original inequality. So when we're looking at what is greater than or equal to 0, we're looking from -6 to 2, and also 3 to infinity. And remember, because our open circles at -6 and 3, that's why we use parentheses there. And the closed circle at 2 allows us to use the bracket and include that number. So up next, example 2, we want to first factor it. So we do have it, quote unquote, equal to 0. So we are good with step 1. We do have a single rational function, so step 2 is good, and we just need to start by factoring. So when we factor that, the numerator is a difference of squares, so we end up with x minus 2, x plus 2, and the denominator, we want to look for what multiplies to 25, adds to negative 10. That would be x minus 5 squared, or x minus 5 times x minus 5, which means our critical points, or our critical values, are going to be 2, -2, and 5. So once we have identified our critical values, we can go ahead and set up our sign chart. So we have -2, 2, and 5. We cannot be equal to 5 because that one is from our denominator, but -2 and 2 are our zeros, so we can be equal to those. However, because our original inequality does not have equal to, we actually still want to use parentheses in our final answer. So now that we have set up our number line, we're going to test values within each interval. So starting on the left, we could test like -5, for example. So -5 minus 2 will be a negative. -5 plus 2, still negative. -5 minus 5 will be a negative, but because that's squared, it'll end up being a positive. So because we have two negatives, that interval will end up being positive. Then our next interval, -2 to 2, we can test 0. So 0 minus 2 will give us a negative, 0 plus 2 will be a positive, and our denominator is always positive because it is squared. And because we have an odd number of negatives, that interval will end up being below the x-axis. So then we check our third interval between 2 and 5. I can check 3. 3 minus 2 is a positive number. 3 plus 2 is positive. And then remember, our denominator is always going to be positive because of that square. So that interval will end up being positive above our x-axis. And then our last interval, we could check, say, like 10. So 10 minus 2 is going to be positive. 10 plus 2, positive. And our denominator, always positive. So that interval is positive, which means we only have one interval that is going to be below our x-axis. So our final answer, and remember, because we are not equal to, we're going to use parentheses for the whole interval. So we're going from -2 to 2 is where our rational function is less than 0. So up next, we have example 3, which is slightly simpler. So we already have 0 by itself. We have a singular rational function. So we can start out by identifying our critical values. There is no critical value from the numerator, and we get x equals 3 from our denominator. So that means our sign chart is only going to have one value, and so we'll only have two intervals to test and see where we are greater than 0. So if we check on the left, we could check 0 itself. Our numerator is always going to be positive because of that 2. 0 minus 3 is going to be a negative, so our left interval is negative. Then on the right side, we could check 5, because 5 is bigger than 3. So our numerator, once again, always positive because of that 2. 5 minus 3 is positive, so our right interval is going to be positive. And since we are looking greater than 0, we do want that right interval, and we cannot include our critical value from our denominator. And even though we can't include it, we wouldn't want to because we're not looking at equal to 0. So our interval would be 3 to infinity because we're going from 3 to the right all the way to infinity. That side of our graph is above the x-axis. So I want you guys to go ahead and try example 4 and example 5 on your own. So be careful identifying your critical values from the numerator and denominator. And then remember, the critical values from your denominator cannot be included in your final answer. So it has to have parentheses instead of brackets. Then we're going to look at example 6. So for number 6, we do have 0 by itself, and we do have a singular rational function. So we get to jump to identifying our critical values. We once again do not have any from the numerator. We just get x equals 1 from our denominator. So I'm going to put an open circle there to remind myself I cannot include that. And then once again, because we only have one critical value, we're only going to have 2 intervals to test on either side of 1. So if I check the left interval, I could check 0. Our numerator is always going to be positive because of that positive 1. Our denominator is always going to be positive because of the square, meaning the left interval will be positive. So now let's check the right interval. And because our critical value is 1, we could check 2 or 3 or 4. Our numerator, once again, is always positive because it's a 1. Denominator also always positive because of the square. So our right interval is positive as well. Well, if we go back to looking at what we were being asked to find, looking at where we are less than or equal to 0, we are not less than 0 anywhere, and because the only place we are equal, we cannot include that critical value. This example has no solution, so you would write no solution. Or you could write it as the empty set. So those both are acceptable answers. So our last example, we have the graph of a rational function f shown in the picture above. We're going to use that graph to solve the following inequalities. So our first one is asking where f of x is less than or equal to 0. So remember, that is below or on the x-axis. And we're only looking at on the x-axis because of that equal to part. So identifying our zeros first at 1 and 2, and then looking at where we're below the x-axis, so the left side of -1, until you reach your vertical asymptote at -3. But because that's a vertical asymptote, we will never actually get to -3. So we will use a parenthesis. And then because we want to be equal to 0, we will use a bracket around the -1. And then we become equal to 0 again at 2 and are below the x-axis all the way until our next vertical asymptote at 3. And once again, because it's a vertical asymptote, we're going to use parentheses. So our next part, B, is asking where f of x is greater than 0. So this should be the exact opposite of everything we just wrote. However, we have to be careful because of our asymptotes. So where we are greater than 0 or above the x-axis, So we start at negative infinity and go all the way to negative 3. And because at negative 3 we have a vertical asymptote, we have to use parentheses. And then we are positive again between negative 1 and 2. And we're using parentheses because we are not equal to this time. And then we have one more section where we are above the x-axis up on this right section. So starting at our last vertical asymptote at 3 and going all the way right to infinity. So as a reminder, when we are identifying these intervals, we are using x values. And the reason we answer with x values is because it's asking us where is y less than or greater than 0. So we have to respond with x because we're being asked about y. So our last example is asking us where f of x is greater than or equal to 1. So instead of looking at above or below the x-axis, we're looking at above or below, just above 1. And if we look at 1, that's where our horizontal asymptote is. And above our horizontal asymptote is our far left and far right piece of our rational function. So we get to use the first and last piece from part B. So we are greater than 1 from negative infinity to negative 3, and from 3 to infinity. And the reason we are using parentheses is because at negative 3 and 3, we have vertical asymptotes, which we will never touch or cross. So we will never actually get to that asymptote and be equal to 3. And also because 1 is a horizontal asymptote, we will never actually reach 1, which is why this whole thing is using parentheses. So as a reminder, when we are solving inequalities, you want to make sure your rational function is on one side by itself as a singular fraction. Find your critical values, which is where your numerator and denominator equal 0. Put those on your number line and create a sign chart to help you see where your rational function is greater than or less than 0. Hope this helps, and I'll see you guys next time in class.